Hey, it's been a while. If this is your first time here, hi, I'm a guy named Michael, and I, sometimes, make science-related videos within the context of video games, mostly paleontology-centric. This isn't what I was planning to publish next after the first upload, which... How the hell has it been more than a year? But I couldn't pass up an opportunity that presented itself this spring to showcase my work. This video was actually a graded assignment for a community ecology course I took this past semester at university, which basically involved us searching for a paper related to community ecology, published in the last 10 years, summarizing said paper, and forming a research proposal based on its findings in a 6-minute presentation. Why am I sharing this, you may ask? Well, long story short, I told my professor during their office hours that I make YouTube videos on the side, which caught their interest, so I sent them my first video, Splatoon's Secret Sea Monster, which y'all should watch, by the way. It took me a year and a half to complete it. And they loved it. And with their permission, I'm able to share this assignment with all of you guys, and end a nearly year-long content drought. So, without further ado, here's my final recorded presentation discussing Japanese rhinoceros beetle sexual selection and Caustidae moth larvae. The paper selected as inspiration for this assignment revolves around sexual selection and how that affects weapon size in recently diverged populations of these beetles. But before we go further, I do think a brief beetle bio is in order. The Japanese rhinoceros beetle, or kabutomushi, is a large scarab found across East Asia, including Taiwan, China, the Korean Peninsula, and, well, Japan. Their grubs feed on wood pulp and humus to grow, while adults feed on sugar-rich fruits, sap, and nectar to avoid competition with each other. Males and females are sexually dimorphic, and males famously duel with each other with their elaborate horns during their mating season. They are short-lived, however, only living for a year, most of which is spent developing as a grub, which is necessary for the males because, relevant to this paper, horn length is not directly heritable and is dependent on the larval form's nutritional levels when growing up. Despite these growing pains, these beetles are widely popular as pets in East Asia and are a useful model organism for research due to being very easy to raise. Oh yeah, the Pokémon Heracross is based on this beetle. He's going to be helping out in this video. Back to the paper, the main objective was to determine how the beetle's local habitat and breeding ecology create these differences in horn size. Populations across their range can vary in terms of relative horn length and can alter the odds of successfully acquiring a mate. Since we also know horn length is determined by larval nutritional levels, which are correlated with their surrounding environment, two hypotheses were proposed based on these factors. 1. Horn length contributes more to winning fights in longhorn populations compared to shorthorn populations, and 2. Winning fights is more likely to translate into mating success in longhorn populations than in shorthorn populations. So what were their methods? The authors first identified 5 populations for research, 2 in Taiwan and 3 along the Japanese archipelago, representing different and recently diverged populations. Because Taiwan is closer to the equator, the beetles breed 2 months earlier than in Japan, allowing them to observe mating behavior at 2 different locations per year, 2 years total. The beetles will congregate at trees at night to fight and mate, and the authors quantified the number of host trees and territories occupied. Individual beetles were gently caught for horn and body measurements to be calculated and correlated between their overall fight success. After crunching all the data collected, here's what they found. In short, it turned out that it was resource availability and how the males monopolized them that was the biggest driver of sexual selection. Populations with more available resources means less competition, resulting in smaller horns, whereas populations with fewer resources available equated to more competition and larger horns. You need a large horn to protect your patch, and longer horns always resulted in a higher win rate regardless of the population studied. Interesting for sure, but what does any of this have to do with community ecology? Good question. I just chose this paper because I like evolutionary biology. So I decided to look further into the literature for some inspiration and ultimately found something. Turns out, male beetles don't just monopolize any regular territory, they more specifically monopolize tree sap holes. Strangely though, longhorn populations don't make the holes themselves, because they congregate around oak trees whose bark is very hard to carve. Conversely, shorthorn populations can make these holes themselves because they congregate around ash and bay trees whose bark is much easier to carve and thus can create patches for themselves. So, where do the oak tree holes come from? Enter Causidae, aka carpenter worms, a clade of moths whose caterpillars burrow into trees to feed on sap and wood to grow and pupate. These insects have been found to increase sap exudation in oak trees through their burrowing, providing greater access to a valuable resource for many invertebrates. Flies, wasps, butterflies, moths, and, you guessed it, the Japanese rhinoceros beetle all benefit from their presence. Which brings me to my research proposal, which asks, how could the disappearance of carpenter worms influence the behavior of Japanese rhinoceros beetles? This is more of an exploratory what-if scenario, looking to see what would happen if carpenter worms were not present to create sap holes for the beetles to monopolize and fight over. We see in other insects, like this Alcon blue butterfly that rely on other species of plant and insect for reproduction, can be threatened with extinction if one facilitator of their life cycle becomes unstable. While not at the same extreme as the Alcon blue, could something similar happen to the beetles if the carpenter worms decline in number? And do the rules of their mating game change accordingly with their absence? To answer this, take a look at my proposed methods. We can create a microcosm setup with a control group with feeding patches represented by artificial beetle jelly sap or fruits, and an experimental group without feeding patches to simulate the absence of carpenter worms. Between 60 to 80 beetles will be cultivated and divided into these groups, attempting to replicate the number of beetles observed in prior studies. Once they pupate, we count the number of males and females and record the number of aggregations and challenges between rival males per night over the 2-month breeding season. Once the population reproduces, run a second trial the following year. We won't know what exactly will happen in this study since this hasn't been performed before to my knowledge, but we can predict that the experimental group will either still fight, albeit much less frequently, or not fight at all due to no patches to monopolize. Knowing what will happen in this scenario is important as it helps further establish known interspecies relationships, assesses the potential impact one species has on another, serves as a call for further research on an understudied group of animals, and highlights potential vulnerabilities in the beetle's ecology. Also, it's just plain interesting to learn about. And that's that. So, what did you think? Anything you liked about it or any improvements to be made? Let me know in the comments. Helps boost engagement. Also, big shoutouts to my friend Turret for creating these stills and animatics of my self-insert. These are awesome. And if you like what you saw, do me a solid and like and subscribe. There's more coming. I'll hopefully have something before the end of the summer. I swear, I am cooking. See you guys then.